Welcome to Closer to Truth. I'm speaking with astrophysicist and science visionary Janna Levin. Welcome, Janna. I've
Thanks.
admired your work as a scientist, especially on black holes, and as a science communicator. We'll be talking about both, but let's start with the breathtaking discoveries of the James Webb Space Telescope, literally breathtaking, and their implications for cosmology. Early galaxies, larger, earlier, more structured, more numerous than expected. Black holes, early black holes, your specialty, larger and more than expected. What are your favorites of the JWST discoveries?
Well, it's really the overall picture that's being painted that I think is so incredibly exciting. There was a time when we didn't really believe black holes were real astrophysical objects. It was quite stunning to discover nature figured out a way to make black holes. They were considered just a mathematical oddity, an imaginary scenario. And then came supermassive black holes. We don't know where they come from. They were already startling. And now James Webb has really sort of secured the role of supermassive black holes in their formation of galaxies and their importance in the early universe. And that's been pretty thrilling, I'd say.
Great. Now, some people are using that information, that the surprise of supermassive black hole, for example, as justification for their own theories, which have been bubbling for a long time. They say it's blowing up cosmology. That it's really created a cottage industry of Big Bang deniers. Using JWST information, specifically on supermassive black holes, to use that to deny the standard model of cosmology, deny the lambda cold dark matter model, deny inflation, and all of that. What do you make of that?
Well, I have an inbox full of people's theories. I mean, it's gotten worse. I think my Twitter account is loaded with theories, and my Instagram, I even get people's theories. So I tend to filter them out. I'll be honest, I have not followed any kind of controversy about it. I think that the real scientific issues are interesting. Scientists like to be wrong. And we did not predict supermassive black holes. That's fantastic to discover them, to try to understand the role that they have in cosmology and maybe how the early universe is different from the standard picture. Oh, that's very exciting. There was a time where we did not know that there was dark energy. We did not know there was dark matter. There was nothing wrong with exploring valid, hard, interesting theories that challenge your preconceptions and challenge your intuition. I love that stuff. Very open to it all. Now,
Great.
the problem with a lot of the conspiracy theories is they're not rooted in anything. They're not rooted in a mathematical model. They're not rooted in scientific data. They're really rooted in a kind of romance with just word language. They think we're all just slapping words together out there and making it sound snappy, but we're doing a lot of really intense hard work. Most of our own ideas are killed on the page by us before it even comes public. So they're not putting themselves through the same process.
Good. Well, we'll get into all of this in detail, but first, let me give a more proper biography. Janna Levin is professor of physics and astronomy at Barnard College of Columbia University. She is the chair and founding director of the Science Studios at Pioneer Works, an amazing place in Brooklyn, and the presenter of Nova's Black Hole Apocalypse, which aired on PBS. Janna's research focuses on black holes, the cosmology of extra dimensions, and gravitational waves. Her books include Black Hole Survival Guide, Black Hole Blues, and Other Songs from Outer Space, which was on the amazing discovery of gravitational waves, How the Universe Got Its Spots, and a novel, A Madman Dreams of Turing Machines. Janet, let's begin with a real in-depth approach to black holes. And I have a number of questions, but let's start with your very nice statement that black holes are nothing, not a thing. What do you mean by that?
Yeah, I find that to be a fascinating twist in kind of refocusing, shucking away the myths about black holes. People imagine black holes are incredibly dense objects. And to some extent, that is one way in which black holes form, a very dense object forms. But once, let's say, a collapsing star, as the canonical example, gets so dense that the event horizon forms, that is to say, the gravity is so strong that not even light can escape, an event horizon forms, the star can no more sit there as a dense object than it itself can race outward at the speed of light. So the material that made the event horizon, that formed it in the first place, is forced to continue to fall. It leaves the event horizon behind, just an empty spacetime. There's no longer a star there, there's no material there. And that's really quite fascinating. If you were an astronaut and you were to go up to the event horizon and you're about to cross and you're about to fall through, there's nothing there.
Hmm.
It's an empty shadow. It's equivalent to stepping into the shadow of a tree.
Hmm.
And I find that utterly remarkable. Black holes really are nothing. There's nothing there. They're an empty space-time. In some sense, a black hole is as much a place as it is a thing.
Yeah, and that's a wonderful characterization. Now let's deal with some of the specific kinds of ways of classifying black holes. So let's start with something simple: the size, or really the mass of it, the event horizon. What are the different? What's the range of size?
Well, that has been also quite a surprise for many years, ever since the gravitational wave discovery, where they recorded the sound of space-time ringing from the collision of two black holes. Very obscure, difficult to understand project, but the discoveries were very surprising that black holes came in this range of masses. I'm not going to say I anticipated that range of masses, but I was certainly open to it.
Hmm.
I think people believe black holes were mostly going to be pretty small. So if you have a big, heavy star, very massive star, it collapses under its own weight. It very well might supernova. And then the remnant core it leaves behind collapses down into a black hole. So what you've got left could be anywhere. I would say 5, 6 is very, very small, times the mass of the sun, solar masses. 5 or 6 times the solar masses would be extremely small. 10 is kind of a standard size. People were suspicious about 20 or 30, but now we see that the black holes are regularly coming in 50, 60, 80, maybe even 100, 120 times the mass of the sun. And then they start to get into a range where we don't have good ways of detecting them. So there might be a whole bunch, 300 times the mass of the sun, we don't really know.
Hmm.
And then it comes to the supermassive black holes. Now, these other ones that I'm describing that could get up to hundreds, they might form as a dust state of a star and then collide and merge and get bigger
Hmm.
over many collisions over the history of the universe. And that's how they got to be their large size. It's not as though a star collapsed and was 100 times the mass of the sun in its core.
Hmm.
I don't think. But the supermassives are not forming this way. They're definitely forming a different way. So the supermassives are their own category. They really are. And they seem to form much earlier in the universe's history, within the first few million years.
Amazing.
Amazing, yeah.
Other characteristics: spin, rotation,
Yeah. So black holes are
charge.
characterized by very, very few numbers. So black holes are unlike any other material object in the universe. So I can talk about chairs, but they have infinite permutations of properties. And black holes aren't like that. They have a very short list of properties. You can characterize a black hole by its electric charge, its rotational spin, and its mass. That's essentially it.
Hmm.
I can make more complicated theories where maybe I have a different kind of charge, but essentially that's it. Charge, mass, spin. That's almost what you would say about a fundamental particle. You would say, I can characterize this fundamental particle in nature by 3 quantum numbers: its charge, its mass, and its spin. That would be a normal thing to describe with fundamental particles. Very unusual for black holes, but it's also a suggestion that black holes are in some sense also like fundamental particles. And they really might be. They really might have a role in the particle spectrum of absolutely fundamental theories and fundamental particles.
Boy, that is
I tried to, sorry, go
profound.
ahead, Robert. Yeah.
It's really profound.
It's very profound. And the other implication of this is that they're flawless, right? So if I go up to a black hole and I try to throw a mountain on it and make it lumpy, so I can say, that's my black hole, I've put a landmark on it, I can now identify it. The black hole will not tolerate that landmark because it can only be characterized by its mass, its charge, and its spin. It cannot also be characterized as having a lump the shape of Mount Everest, right? So what it will do is it will actually shake off that imperfection. It will absorb what it can, and it will throw off some of the material, and it will radiate away the imperfections in gravitational waves, ripples in the shape of the space-time around it, until it settles down to a black hole whose only characteristics are its mass, charge, and spin.
Yeah,
So
amazing.
quite deep.
There's this famous term called no hair
Yes.
that defines its perfection. Basically, says the same thing that you do with a flourish of no hair on it.
Yes.
And you put it nicely in your book. If you put a blemish on it, it won't stick.
It will not. No, it will absolutely shake it off until it looks perfect, essentially.
In terms of formations of black holes, we know the supernova, which is as you said, the canonical case. Gas collapsing, I think now is when the supermassive black holes so early on is another way. How would you characterize the different categories of formation process?
Well, right now, the ones that we think are happening astrophysically is mostly stellar collapse, very heavy stars whose cores survive heavy enough after a supernova explosion to collapse under their own weight and become black holes. You can also take something like a neutron star and pile more material on it. So a neutron star is a core that at the end, in its death state, doesn't quite make it to become a black hole. They're usually about 1.5 times the mass of the sun, and they're just a little bit bigger than a black hole. Black hole that massive would, although we don't think there are any that small, would only be a few kilometers across, 6, 7 kilometers across, something like that. And a supernova is more like 20. So it's a little bit bigger. It's still pretty small. Now, that is a dense state of matter. You go up to the neutron star, that is an unusual and extravagant state of matter. And when you put even a little bit more on it, maybe it has a companion and it's cannibalizing that companion, is splattering material on it, it can be forced over
Mm,
that boundary and become a black hole. Now, the supermassives might be forming directly, skipping stars altogether. They might be forming when the universe was much less dense. And it's surprising, but you can have a big black hole is less dense. It's kind of
mm,
surprising. And so you can make the black hole, a very huge one, out of something very early in the universe, out of something with the density of like air.
yeah.
And it will actually be able to form a black hole. So it is, if they're left undisturbed, you can create these certain unusual circumstances where they might form directly. Now, there's not one other way, there might be many other ways. But if black holes are fundamental particles in some sense, then there are probably microscopic black holes made primordially in the early universe, in
Mhm,
the Big Bang.
mm.
And those black holes are made the same way all the other particles in the primordial soup of the Big Bang are made. They're just part of this primordial soup. So you might have quarks and leptons and electrons and photons and gluons and all of these wild particles and in their highest energy state. And you might also have little microscopic black holes.
And when you say microscopic, you mean like the size of atoms or the size
Like
of a sand grain?
smaller,
Even smaller.
smaller than the size of a proton.
Hmm.
They would be the smallest spatially and the heaviest for their size of the fundamental particles in the spectrum. And that's also the thing, is that black holes are spatially small. So we kind of have this idea, oh, they're huge monsters, but the whole point of a black hole is that they're spatially very, very small
Hmm.
for their heft. And so as a fundamental particle, it would come in smallest and heaviest.
Primordial black holes, that small as fundamental particles, are theoretical. Obviously, none has been detected. But if we were to run in, or if Earth were to run into one of them, what would be the potential impact?
Well, the thinking is that they would evaporate through the Hawking radiation, which is a process that Stephen Hawking became so famous for discovering.
Right. We'll be talking about that. Hmm.
Yeah, another irony about black holes is the smaller they are, the hotter they are in terms of their Hawking radiation. So the primordial ones, because they're so tiny, they're actually like firecrackers or TNT. They're like little bombs. So they would explode, presumably, and would not be lingering around anymore.
Good. Okay, let's get into some very specific questions. I think we were all just dumbfounded by the creation of LIGO and being able to discern gravitational waves. And I think the data is that they can measure the change in space-time to 1/10,000th the radius or diameter of a proton, which is absolutely incredible. But I just want to ask you one specific question, that from the very brief gravitational waves that we see, the chirping, as you say, the songs of the gravitational waves, and they're very short. How can we be so accurate in determining the mass and nature of the colliding objects, be they two black holes or two neutron stars, neutron star black holes, and even their pre-merger orbital speeds? All of this is derived from just that short chirp.
It's an excellent question. There's a whole history of this that predates the LIGO experiment. There's a famous mathematical paper that's titled something to the effect, "Can I hear the shape of a drum?"
Hmm.
And the idea is, if I record the waveform of a ringing drum, can I determine the boundary of the drum, its size, its shape, the speed, the mallets on it? Like, can I reconstruct all of these details? And to a large extent, you really can. Now, there's some degeneracies, meaning I can't completely separate every single aspect of it. But what people did is they predicted the mallets on the drum. The mallets are the neutron stars, the black holes, whatever objects we might imagine are out there, or a black hole and a neutron star, and the motions. Exactly what you said. The orbital speed, that's the mallet on the drum, and you can imagine your ear is actually not bad at doing that. Your ear is not bad at determining that it's a big drum with a slow mallet. You can absolutely deconstruct the waveform and know if it's a fast mallet and a high pitched taut
Hmm.
drum, right? So a lot of the theoretical work leading up to LIGO was about building these waveforms. We call it a process of matched filtering, where you have these filters that you've constructed. This is what this will sound like.
Hmm.
This is what that will sound like. And then you run it alongside the data and you try to get them to match and pull the signal out, because it's part of the difficulty is that the signal's very, very, very low, even for the instrument,
Sure, sure,
compared to the noise.
sure.
So yeah, you will find yourself, you're a pretty good matched filter. You're into neuroscience and things like this. You can hear the person you're listening for at a cocktail party pretty well, even if it's noisy.
Hmm.
We do this a lot in different data sciences, and LIGO just did a really terrific job of the data analysis.
Yeah, between LIGO and JWST, I mean, those are two of the greatest instruments in human history, and
Absolutely.
just are breathtaking in
I
their
just
capability.
Yeah, I just have to mention, if you, since you're saying that about the JWST, it had an enormous number of individual points of failure. I've forgotten if it's between 100 or 300,
Yeah,
but meaning if that one of those
right.
100 to 300 things went wrong, the entire instrument was doomed. And that level of confidence and successful engineering, it really is a testament to what we can do internationally if we pool together on and are committed to a project. I mean, imagine what we could do if we committed to something else,
Good. Yeah, I agree. We'll start with peace in the world, but that's a different
like
subject.
peace in the world, for example.
Okay, let's talk about the event horizon. And one of the startling things that I still am astonished by is the warping of time, warping of space. I can sort of get my
Mm-hmm.
head around, but time gives me more trouble.
Mm-hmm.
And so time radically warps such that as something, observer, whatever, doesn't matter, approaches the event horizon, a third party observer watching that will never see it past the horizon, but just get slower and slower and slower. I think infinitely, asymptotically infinite,
Mm-hmm.
and never get there. Whereas the object itself, whether it's a human or anything else, would just pass through as if and notice nothing special.
Mm-hmm.
So how do you reconcile those two ideas with the
Yeah.
concept of time?
Well, it's a big one. I will amend one small statement, which is that eventually everybody will agree it does cross the event horizon. So I can give you the example. I have two huge black holes. LIGO sees them merge. They
Yeah,
cross each other's event horizons, right? The
right,
event
right.
horizons literally bubble and distort. And then in the same process of trying to restore its perfection, it rings off the gravitational waves.
Mm.
and it settles down to one perfect black hole again. And that happens in short order. Not only does it not look like it takes infinity, it happens fast. And the reason is because this idea of it taking an infinite amount of time is true if the particle falling in is infinitesimally small in its mass, so that it has basically no gravitational effect of its own.
Mm.
It's 100% a little test particle that has no impact of its own on the black hole. Now, you can never really reach that limit. Whether it's a spacecraft, it has some mass, tiny, and gravity is very weak. And it would take a very, very long time. So let's say you were throwing an astronaut in a spacecraft across the event horizon. Uh, it would take maybe longer than your lifetime, maybe longer than the Earth's lifetime. But eventually, it would actually bubble in. And in a finite time, if anyone's left to watch, they would say, oh, it's gone.
Okay,
And
that contradicts a lot of the sort of the pop science on it.
well, it's the pop science is correct for this perfect massless particle that has
Oh,
no impact on space-time, of which there are none.
yeah. Okay.
Because even light, which is massless, has energy, and
Sure.
energy deforms space-time. So
Sure.
even light will eventually fall in.
Okay.
But just to say, it might as well be infinity. The smaller and smaller I make that mass, I'm sending in a postage stamp with a little computer on it, sending me signals. And that would take, very close to a much longer, maybe, I don't know, a very big number, let's just say, and it might as well call it infinite. Now, yet, you're absolutely right. For that postage stamp, uh, it can happen in a fraction of a second. So there's a disconnect between the passage of time for this. If there's a clock on that little computer, the clock will think it's only been a few seconds, and the clock will be right
Yeah.
that in its frame of reference, it's only been a few seconds, while for some astronaut watching from far away, it's been 10 billion years.
Yeah.
Or
Amazing.
something
I
like
mean,
that.
this is a ringing, pardon the pun, ringing verification of Einstein's general relativity.
Well, what else is your cell phone has to use this principle. Now, we're not near an event horizon, but even near the Earth, there's a slowing of the passage of time just from the Earth. And the denser the object, the slower it would be. Neutron star would be really slow. You have to get all the way to a black hole for it to be this kind of catastrophic misalignment. But there's also spacecraft that are doing our Wi-Fi signals are also cruising pretty fast in their orbits, and you have to compensate
Yeah.
for both relativistic effects. And when you incorporate both, you will notice that there is a misalignment between the passage of time on the spacecraft that's getting our GPS signals or our phone signals and our passage of time here on Earth. And it has to use that correction in order for Uber to find you on the right corner.
Right.
Otherwise, you're going to be off by kilometers
Right.
because the speed of light is so great that if your time is off by a tiny bit, it's a big deal. You're not going to find Uber on the exact street corner if you do not correct for relativity.
Yeah. Amazing.
Yeah,
Okay, now once you're inside the horizon, another startling um, realization is that the singularity, which is the core concept of a black hole, is not a location in space, like in the middle of it, but
yeah,
really a point in time in the future, and
yeah.
thus, and therefore, it's impossible to avoid because it's a point in time, not a point in space.
Yeah, that's really spectacular. So, from the outside, we imagine, let's say the black hole's not spinning, and I have this spherical event horizon, and I imagine a point in the middle is the singularity. It's
Right,
spatial. Clearly, it's the center of a sphere.
right,
But that's really not true for anyone who is falling in. When one way to think about why time is slowing down is to imagine that space and time are kind of like left and right, let's say.
hmm,
So I can, right now, I don't know if the camera's really sending us mirror images, but let's pretend you and I are facing each other. So my left is is your right, and my right is your left. We're misaligned. And I can rotate into your right, out of your right. And so space time is like that, but it's not a spatial rotation. It's called a space time rotation. What's happening is as you're falling in, your space is rotating into time, and their time is rotating into space. So that at some point, their time has rotated totally out of your time. That's why it looks like it stops and completely into your space. So, what you're calling a point in the center in space, the infalling astronaut is measuring as a point in the future. And that is very well substantiated from all of the mathematical models we understand, that you can no more avoid the singularity when you get inside. It's not like you can fly around in circles and you don't ever have to get there and you can hover with all the fuel in the world. You cannot do that. It is at a predictable, finite point in your future, and you will hit that singularity.
And the rotation between space and time obviously is a product of the unification of space time, again Einsteinian,
Mm-hmm.
and that is that is demonstrated mathematically. But are there any observational confirmations of that?
Well, the GPS unit is an example of a small rotation between spacetimes, you could say.
Okay, all right.
Yep, absolutely. And we have particles that are coming from space, things like cosmic rays that are traveling at incredible speeds. And in fact, you can have a particle that lives for a fraction of a second in a laboratory before it decays. It has a very short lifetime. But if you boost it near the speed of light past your laboratory, it will appear to you that it's lasted for minutes.
Mm,
And for the particle itself, it still has that very short lifetime.
yeah.
It decays. So that rotation, that misalignment is absolutely measurable.
Another incredible fact when you're within the event horizon is that the mass of the black hole, the full mass, is always ahead of you, no matter how far you go. And that just seems impossible to understand.
That is the whole reason why black holes are so extraordinary. You can have a black hole 10 times the mass of the sun, but you can also have a star 10 times the mass of the sun. So what's the big deal? The point is if you approach that star, it would, of course, be incendiary if you had some mechanism to survive immolation by the star. As you moved inside the atmosphere of the star, you're leaving some of that mass behind you,
Hmm, hmm.
right? And so, what's pulling on you? It's a beautiful theorem in all of gravity theory, even predating Einstein, that all that matters if it's spherically symmetric is what's in front of you. And so, as the sphere in front of you gets smaller, if the mass gets smaller, the gravitational pull drops off,
Hmm.
gets weaker and weaker and weaker. The craziest thing about the black hole is that it never drops off. You never leave any of that mass behind you. It's always in front of you because it's crushed interior to that event horizon. So the gravitational pull reaches dramatic proportions that it never does with any other kind of object, even one of the same mass. And that's the reason, because it never drops off. It's always in front of you.
Okay, let's discuss what we mean by never. Is it the same kind of never that that a something entering the event horizon never gets to it? Is it that same kind of never? So that never means 10 to the 10 to the x years,
I
or it really means never.
Yeah, I the truth is we don't know exactly what happens when you get close enough to the singularity that our known laws of physics are no longer
Okay,
operating
all right, that's fair.
properly. So I can't say. So yeah, maybe it's not never. Maybe I run into a quantum remnant in the interior and it's a real thing and I can touch it and hammer on it and there's no singularity and there's this bizarre quantum tesseract crazy thing, like interstellar. But it's also possible that something much stranger even than that happens. And that involves string theories and wormholes connecting the interior and the exterior. And there's all kinds of things on the table now for trying to understand what the reality is of what ultimately happens to the matter that falls into a
Yeah,
black hole.
it's the greatest test bed for fundamental physics that can be imaginable.
Absolutely.
I think you have in your book the 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 energies that you need to explore these fundamental physics, and that black holes can give us are like 10 million to the 10 million billion times the power of the Large Hadron Collider, or some number like
Yeah,
that. In other words,
the proportions are completely staggering, and I think you're talking about like Black Hole Survival Guide right now, and that what what's so fascinating there is you can speak about black holes totally in the abstract. You don't have to be talking about specific ones.
Hmm.
And that's another, this is part of that whole thing, that this hint about black holes, that they're somehow telling us something about the fundamental theory.
Good. A question I had when I first saw that remarkable Event Horizon Telescope photo
Mhm.
of a black hole with a black center and the ring of light around it. I I was first surprised that the ring was not symmetrical because, given the perfection of a black hole, that it is absolutely hairless, um,
Mhm.
and gravity would make it a round shape, which we do see. Why
Mhm.
the light is asymmetrical,
Right. Well, that's a good question too. With the light that you're receiving is coming from outside the black hole,
right?
from accretion and matter that's fallen onto an orbit around the black hole, collided with itself, smacking at really high energies. You know, you drop a penny from the Empire State Building, it is coming down really hard and fast when it hits. You imagine something makes it all the way to this tiny target of the black hole, it splatters onto it, very high energy stuff. That stuff's not perfect.
Right,
It's
right.
around the black hole, and and so it has its own. There's turbulence. It's colliding with itself. It can come from one side predominantly. So it can take a while for that to smooth out.
So it's
Um,
the asymmetry of the disks or the stuff that's circulating around the black hole that is causing the asymmetry.
that's right. And there's a lot of things that it gets really complicated. Unlike the black hole again, there's a lot of things that can be
Right,
going on.
right.
Kind of the material, the magnetic fields that are threaded in the material, all of that really dictates whether there's tubes of magnetic flux, and what's going on there can be very complicated and very dramatic. And even what it's made of, if it's high iron or if it's made of other elements. But also, you have to remember it's very few pixels.
Yes, right, right.
So the Event Horizon Telescope is taking very, very few pixels worth of data. And it could be a long, long time before maybe we realize it's not quite as lumpy as it looks. And also, part of what you're seeing is, if you imagine a flat disk like the rings of Saturn. Now, this might be hot and crazy with magnetic fields and much more energetic, but it might well be in a very thin disk like that.
Mm,
The reason why it's casting the shadow of the black hole, if you imagine the black hole against a dark sky with that disk, you wouldn't see the black hole.
of course.
All you'd see is the disk.
Right.
So the reason you can see the black hole is because the light, which is trying to escape from that ring, some of it gets bent right around the top
Mm,
and comes at you. And it gives the illusion that the ring is enveloping the black hole on all sides. And it's really not. And so what you're seeing is a direct consequence of the bending of the path of light on the curved space-time, following the extreme curves in space. So instead of the light, like Saturn's rings, just escaping freely, a lot of them get wrapped back, redirected towards the telescope, and it creates this wonderful phenomenon. It gives us the gift of casting the shadow
mm.
of the black hole.
Good. Let's talk very briefly about Hawking radiation, the incredible discovery that even though nothing can escape a black hole, especially light, Hawking radiation does show that over eons of time, 10 to
Mhm.
the 100th years or whatever, black holes can evaporate due to this Hawking radiation. And the question I have is that the way that's popularly phrased is through quantum particle, antiparticle coming into existence. If they're right at the horizon, one would go in, the negative would go in, the positive would go out, and that would reduce. That would cause it. But that many say is a wrong explanation. The Hawking radiation is right, but it's not something that's happening at the event horizon, but rather near the black hole, and it's an interaction of quantum fields. So, just want to get a clear clarification of the mechanism.
So the original mechanism that you're describing, two particles are created, that actually isn't that bad a description of the low energy quantum phenomena. It's pretty good actually. But the what's wrong with the description is there's no negative mass. An antiparticle doesn't have negative mass of a particle.
Hmm.
So a lot of people will have this story. Oh, two particles are created in the vacuum because of Heisenberg's uncertainty principle. I can never be sure that there aren't two particles. So as long as two come together, that reproduce the conditions of the vacuum, meaning they have equal and opposite charges, and all of that will be canceled so it looks like the nothingness of the vacuum. It's not a positive mass and a negative mass. Antimatter has positive mass. Now, what you're doing is you're using the Heisenberg uncertainty principle to say, oh, I can create some energy, positive real energy. I just have to do it in a very, very, very short time, according to Heisenberg's uncertainty principle. And there's nothing wrong with it because I can't be sure it's not there. If I can't be sure it's there, right? So what the black hole does is it steals one. So as these particles are created, it steals one behind the event horizon. It can be the particle, it doesn't have to be the antiparticle. Now, what makes it seem to the black hole like negative mass has to do with this rotation of space-time. What I mean by mass is I mean kinetic energy in time, okay? And that can never be negative. We're always going forward. But what the black hole, by seeing the space-time rotation, it thinks that mass can be negative energy in space, and that's fine. I can move in a negative direction or a positive direction in space. I can't do that in time. So it's because of this rotation of space-time that the black hole says, that's not a positive energy particle. Sure, it's a positive energy particle, but it's contributing negative momentum and reducing the mass of the black hole. It's actually a very subtle process, but there's nothing wrong with that description. However, it's not the high energy description.
Oh, okay, great. And the energy is lost through the radiation of gravitational waves?
So it abandoned, well, it can be those particles. So this pair is created, one gets stolen by the black hole, it interprets it as contributing negative mass to the black hole. The black hole gets a little lighter, and now this other particle can't disappear because it doesn't have the right conditions of the vacuum. It's charged, it can't disappear, it has no partner. And so it's free to escape. And so it does, it escapes. And that's what we mean by the radiation.
Right.
Very subtle, unbelievable discovery. Really insane. It's one of these things. It's just, how did he even believe it when he was doing it?
Yeah, amazing. I don't want to talk a lot about the information paradox because we read, every month or so another article about it. I just want to get your opinion. Has it been solved or not? I can't decide.
I would say that there's real compelling evidence how the solution might go. It has not been solved in the sense that I cannot calculate when the information comes out or how exactly. But here's the unbelievably compelling evidence, and that is really this discovery. Many people contributed to this, so I don't really love the hero isolating the one person, but Juan Maldacena did write an incredible paper, and it really changed the whole conversation. And his observation was, imagine a universe like ours. It doesn't have to be exactly like ours, but it's a universe. It has gravity in it. It has quantum mechanics. It has this crisis of black holes. It has the mystery of their evaporation, which we haven't exactly stated, but if black holes can evaporate through this process without anything ever coming from the inside out, where did all the information go? That's the problem, and that's a real crisis for quantum mechanics. And if quantum mechanics is true, information cannot be lost. So something's wrong. Either quantum mechanics is wrong, or the theory of gravity is not fully worked out. We know it's not. Now, what Maldacena did, which is so important, he said, okay, yeah, here's this universe with this crisis in it, that the information, is it getting out? Is it not getting out? People are fighting and debating, but it's equivalent, he said, mathematically, theoretically, in physics, in principle, to a universe on the boundary, a lower dimensional universe that has no gravity in it whatsoever. It is purely a quantum universe, and they're equivalent. Meaning there's exact descriptions. And it's silly to argue which one's the real universe. And when you get to that level of the mathematics, what do you mean by the real universe? They're equal descriptions. Now, if that's true, and it holds up a lot of scrutiny, then the quantum mechanical universe has no information loss problem. It just doesn't. There's no black holes, there's no gravity. It's the same universe in a different description, but in that description, Information is never lost because quantum mechanics forbids that from
Mm.
happening. Therefore, somehow the information must get out in the other description.
Yeah, so terrific explanation. Okay,
Crazy.
Jana, the concept of the singularity is so powerful and so significant. What I'm wondering about is the similarities and differences between the singularity of black holes, which we're getting a great deal of understanding, not complete, obviously, and the singularity that we assume that was prior to the Big Bang and cosmic inflation. We're using the same term, singularity, but
Mhm.
and so I can figure out the similarities, but what are the
Yeah.
differences?
Well, the Big Bang singularity is not shielded from us. We see it in the sense that the light comes out everywhere.
Oh,
It's not shielded behind an event horizon. That's very interesting. Now, some people have tried to sew the space times together like you'd sew a quilt together. So I take a black hole space time with its exterior event horizon, shielding from those of us who live outside the event horizon from the singularity on the inside. And like sewing fabric together, it tries to sew it onto a Big Bang space time.
mm,
Now, that can be done, meaning the fabric will lie flat. It will, not literally flat, but it will join together smoothly. You will have all the kind of criteria you want for sewing something together smooth and nicely. It's not puckered or buckled or resisting being sewn together. So that's intriguing. In that very, very early days when people were thinking about space-time in that way, it was as though you were really saying you had an entire universe inside the event horizon.
mm,
So it could be 10 kilometers across on the outside. But because of the way the curvature of space-time works, it could be as big as a universe on the inside.
right,
And it's not really inside, it's really connecting to a different, it's what's called a white hole
mm,
sometimes. So it's blowing all the matter out without the event horizon into a white hole.
mm.
You got to kind of love that idea, but it hasn't really survived. And it hasn't survived meaning there is no singularity, you really go blown out into a new universe, and all of that matter that fell in finds life somewhere else in the large multiverse ecosystem.
It's very poetic.
It's very poetic, but it's very hard for subtle technical reasons to really stand behind it.
Hmm.
Like, why wouldn't it happen all the time? It seems like it would be entropically high, therefore unstable, likely, and it doesn't seem like it's likely because it's not happening all the time. So there's a lot of subtle arguments why that kind of fell to the wayside. It's not really central to the conversations